Okay, in this video, we're going to be talking about real-life applications of exponential growth and decay. Exponential growth occurs when a quantity exponentially increases over time. Now, the formula for exponential growth, and again, this is a function of time. It's over time, so we're going to be plugging in a time after 1 year, after 2 years. But we have a starting point and then 1 plus r raised to the t power. Now, exponential decay looks a lot like the exponential growth. However, it is a function of time as well. You're going to have a starting value, and then you have 1 minus r raised to the t power. Now, let's talk about why the 1 plus r and why 1 minus r. If something's growing at a rate of 25%, that means it used to be 100%, but now it is 125% of what it used to be. Again, 25% is 0.25 as a decimal. So why do you have the 1 plus r? Well, for this reason. It's 1 plus the new decimal. You could actually put 100% plus the rate and then change it to decimal form. Well, what about the 1 minus r? Well, what if something shrinks by a rate of 25%? It used to be 100%, but now it is 75% of what it used to be, or 100% minus the decimal version of that. That's where that comes from, the 1 plus r and 1 minus r in your formulas. So A is the initial amount, r is the growth or decay rate, and that needs to be as a decimal, and then t would be the number of years or months or whatever. That's the time. So your first problem, Brooke started her career with an annual salary of $32,000. Each year thereafter, her salary increases by a rate of 2.5%. And notice it says each year thereafter, not just once, but every year it's going to increase by that rate of 2.5%. Write and use an exponential growth function. So let's go ahead and write the function first. It's going to be a function of time. She's going to start at $32,000. She's increasing at a rate of 2.5%, and as a decimal, that's 0.025. So this will be 1 plus 0.025. Let me go ahead and erase that, and I'll actually just draw from there, and then raise to the 2 power. And we can clean that up. That'd be 32,000 times 1.025 raised to the t power, and that is a function of time. We want to know write and use an exponential growth function to find out her salary 30 years later when she retires. So we're finding F of 30. So we started at 32,000, and we're going to increase at that 2.5% for 30 years. We are going to have to type this in our calculator. That's going to be a large decimal, and we find out that F of 30 is 67,000. Whoops. Let me scroll back up. $67,122.16. That's her finishing salary. In 95, a magazine had 14,000 subscribers. The number increased by 40% each year thereafter. So again, 40%, that'd be 0.4 written as a decimal. So let's write a function. Again, it is a function of time. We're plugging in time. We started with 14,000 subscribers, but we increased at a rate of 40%. So we're going to do 1 plus 40%, which would be 1.4. 1 plus 0.4 raised to the power of t. So there's your function. Write and use an exponential growth function to find the number of subscribers in 2016. So 95 was this. 2016, that would be t equals, we're going to have to subtract those two values. That'd be 21. That'd be the 21st year. So we're looking for what is F of 21. That'd be 14,000. Oops. There we go. Times 1.4 raised to the 21st power. And that's going to be about 16,398,978 subscribers, and that would be a good bit of subscribers there. That would be rounded to the nearest whole subscriber. Kay drank an energy beverage with this many milligrams of caffeine. Each hour, the amount decreases by 12%. So therefore, a function of time, it starts with 150 milligrams, but however, it decreases at this rate by 0.12. So instead of being 100%, it is now 12% less. It's after each hour, you then have 88% left. So that's where you do the 1 minus 0.12, which is 0.88, raised to the power of t. How much is left in our system after 8 hours? So we're looking for f of 8. After 8 hours, it started at 150, but you're going to find 88% 8 times, and you're going to be left with 53.95 milligrams. Number 4, the half-life of mercury 197 is 3 days. Write and use an exponential decay function to find the amount of mercury 197 left from a 50-gram sample after 20 days. Now this one is going to be a little bit trickier. Now first off, let's talk about what we mean by half-life. Half-life is the amount of time that it takes, like this is a 50-gram sample. The amount of time it takes for that 50 to turn into half of what it is. And in our case, this is 3 days. Now that same mercury 197, if you had a 10-gram sample, after 3 days, it would then be 5 left. What if it started at 100 grams? Then after 3 days, there would be 50 left. After 3 more days, there would be 25 left. After 3 more days, there would be 12 and a half left. Every 3 days, the amount halves. So now this is an extremely tricky problem here, the way we're going to write our function. F of t is equal to, we're starting with a 50-gram sample. Our rate, we're decreasing by a rate of, from 50 to 25, that is 50%. That's what we mean by half-life. It's cutting it by 50%. So that'd be 1 minus 0.5. Now, here's the tricky part. That happens in 3 days, okay? So we've got to figure out some way to manipulate my time here to where when I plug in a 3, because after 3 days, this is going to decrease by half. So let me rewrite this. That would be 50 times 1 minus 0.5 is 0.5. But that only happens on the 3rd day, and then on the 6th day, and then on the 9th day. So if we were to take our time and divide it by 3, when you plug in a 3 now, 3 divided by 3 is 1. It's going to half it once. When you plug in a 6, we need it to half it twice, and it does. If you plug in a 6, 6 divided by 3, that'll be a 2. That's going to be 50 times 0.5 times 0.5. It halved it twice in 6 days. When you do 9 divided by 3, it should half it 3 times, and it does. 9 divided by 3 would be a 3 here. So therefore, when that happens every 3 days or every 4 days, you'll do your time divided by 3, your time divided by 4, and so on and so forth. And again, that is a fairly tricky problem. We'll talk about other ways to work it later on. So here's my function. So now we want to know how much is left after 20 days. So therefore, we're finding f of 20. So that's going to be 50 times 0.5, and that's gone through, let's say 20 divided by 3. That's gone through 6 half-lives, so it's half 6 times and then a little bit more. So after 20 days, and you can type that in your calculator, 50 times 0.5 to the 23rd power, and you're going to get about 0.49 grams will be left of that original 50 grams. Okay, next up, let's talk about continuous growth. Now, here comes that number that we were talking about that I said appears a lot. It says sometimes a quantity is constantly increasing or decreasing. Now, our previous examples, this was increasing or decreasing yearly. It's growing by 12% a year, or decreasing by 10% a year, or whatever, or halving every 3 days. Now, what if it's continuously, constantly increasing? Sometimes the quantity is constantly increasing or decreasing at an exponential rate, and not just after each year or each month or each day or hour, etc. The formula to the right can be used to find the balance of the account in this case. A equals PE to the RT power, where A is the amount left if you start with P. E is the number we talked about earlier in the chapter, 2.71828. R is your rate of increase or decrease, and then T is the time. If R is positive, that's going to be exponential growth. R is positive for growth models and negative for decay models. Okay, first example. A garbage dumpster starts with 4 pounds of garbage. That's the beginning. That's the P value. Now, in our formula above, that was an A value, so it's kind of mixed up. The amount of garbage increases continuously. That's the key word. That's how we know that we're using a PERT, is anytime you have a continuous increasing. It's increasing by 35% each day from this point forward. Find the amount of garbage in the dumpster after 2 weeks. So it's 35% each day. So you got to be careful when we're talking about 2 weeks. So find the amount if we start with 4 pounds. E to the rate is 35%. So we're going to put the rate as 0.35, change it to a decimal, and then the time, we're going to put a T there. So therefore, there's my formula. So if we want to find out how much is left after 2 weeks, be careful because it's 35% each day. So therefore, to find out 2 weeks, you're going to do 14 days. So therefore, we're going to find A of 14. So we're going to do 4 times E to the 0.35 times 14. If you type this in your calculator, make sure that you multiply these exponents first before you raise e to that power. There's actually an E button on most calculators. It'll either look like this or it'll be just a plain E. And you can use the caret to raise it to a power. When we type that into our calculator, we get 537.16 pounds. So we started with 4 pounds and we're increasing 35% each day. So we went from 4 pounds to over 500 pounds in just 2 weeks. The population of a town is declining. So therefore we're decreasing at a rate of 1.5%. So that's going to be a negative 1.5%. Very important that you understand it's negative. Current population. Okay, this is an A per problem. We're starting with 16,000 people. So A equals P times E raised to the R, which is a negative 0.015. Make sure you change it to a decimal, times time. That's your formula. We are asked to find the population after 8 years. So we are looking for A of 8. So we're going to do 16,000 times E to the negative 0.015 times 8 power. Make sure you raise or multiply these powers together before you do e to that power. Also, make sure that you don't multiply 16,000 by e first. You must raise e to the power first, then multiply it by 16,000, and you're going to get 14,190 people. And again, that's an exponential growth there. That's, again, using the continuous interest there. Logistic growth. Now, this is interesting. It says sometimes a quantity exponentially increases but then levels out, approaching a horizontal asymptote, as you see in this graph here. So we've got an exponential growth, and all of a sudden, let's stop and let's kind of level out there. This is called a logistic growth model. The logistic growth function can be used there as that. To where C is that horizontal asymptote line. You see the C on top. Let's see if it gives, and it doesn't. You don't have to know any of the things that anything stands for. They actually give you everything. It says a disease begins to spread in a town of 20,000 people. So obviously, not more than 20,000 people can catch it. So it's going to have a horizontal asymptote line of 20,000 people. After T days, the number of people who have infected by the disease is modeled by the function below. Using the function, find the number of people infected after 10 days. So all we're asked to find here is what is f of 10. They're just kind of introducing you to a logistics model. So it's going to be 20,000 divided by 1 plus 1,150 e to the negative 0.95 times 10 power. Make sure if you don't have a calculator that does order of operations, make sure you do the exponents first, then you raise e to the power, then you multiply by 1150, then you add 1, then you do 20,000 divided by the answer, and you get about 18,415 people. The population P in millions of a country from 1850 to 2000 is modeled by the equation below, where T is the year since 1850. Use the formula to find the population in 1920. So from 1850 to 1920, that's 70 years. So we're looking for the population 70 years later. So we're simply taking out the T value and we're plugging in 70. Once you do that, and that is just typing it straight into your calculator, you're going to get about 12.19, and that's in million people.